Hello there, and welcome to the Night Science Facts channel. Tonight, we'll be drifting slowly and peacefully upward, away from the ground, away from the noise and warmth of the day, into the vast, ancient, breathtakingly beautiful universe of stars. You have chosen a perfect evening for this journey. Perhaps you are already lying in the dark, the room quiet around you, the day finally behind you. Perhaps there is a window nearby, and beyond it, the sky, and beyond that, so far beyond, that the mind softens at the very attempt to hold the distance. The stars themselves are out there, burning with quiet enormity, just as they have burned every night of your life, and every night of every life that has ever been lived on this small, warm planet. Take a moment now to let yourself arrive fully in this stillness. Let your shoulders release. Let your hands rest open or closed, wherever they have settled. Let the weight of your body sink gently into whatever is supporting you. There is nothing you need to hold up tonight. There is nothing that requires your effort or your attention. The stars above have been there for billions of years, and they will be there long after this night is over. They are in no hurry, and neither are we. Tonight, we will travel across the entire known universe of stellar science. We will begin at the moment when the first stars were born, in the silence following the Big Bang. And we will follow the story of stars across 13 billion years of cosmic history, through their births in vast clouds of gas and dust, through their long, luminous lives, through their extraordinary deaths, and through what they leave behind. We will visit stars so large they strain the imagination, and stars so small and cool they barely qualify for the name. We will explore what stars are made of, how they work, how they end, and what they mean to the universe and to us. We have 100 gentle, unhurried facts waiting for you tonight. Each one is a small window into a cosmos that is simultaneously incomprehensibly vast and, through the patient work of science, increasingly knowable. A cosmos that is, in many ways, the source of everything, including you. So, let your breathing slow. Let the ceiling above you become, in your imagination, a window. And through that window, let the stars begin to appear. Let us begin. It is easy, looking up at a night sky bright with stars, to assume that they have always been there, that the universe has always been luminous with their light. But stars did not exist at the very beginning. In the first moments after the Big Bang, approximately 13.8 billion years ago, the universe contained no stars at all. It was a hot, dense, rapidly expanding plasma of fundamental particles, protons, neutrons, electrons, with no structure, no light sources of its own, and no chemistry beyond the simplest elements. For roughly 200 million years after the Big Bang, a period astronomers sometimes call the Cosmic Dark Ages, the universe expanded and cooled in near total darkness. There were no stars to illuminate the vast clouds of hydrogen and helium gas that drifted through the growing universe. The cosmos was dark and enormous and waiting. Then, slowly, gravity began its work. In regions where the gas was slightly denser than average, that slight extra density pulled in neighboring gas, which increased the density further, which pulled in more gas still. Over millions of years, these regions grew into vast, dense, slowly rotating clouds. And within those clouds, at their densest cores, the first stars began to form. The night sky, which feels so permanent and so ancient, is actually the product of a universe that had to wait a very long time for its lights to turn on. The very first stars to form in the universe, called population 3 stars by astronomers, were almost certainly very different from the stars we see today. Without the heavy elements that exist in the modern universe, elements beyond hydrogen and helium which had to be created inside stars. These first stars formed from pure hydrogen and helium gas, and they grew to enormous sizes. Theoretical models suggest that some population 3 stars may have been hundreds of times more massive than our own Sun, towering, intensely hot objects that burned with extraordinary brightness and furious speed. Where our Sun will live for approximately 10 billion years, these massive early stars may have burned for only a few million years before their fuel was exhausted. No population 3 star has ever been directly observed. They formed and died long before any star we can see today. But their existence is inferred from theory, and traces of their influence can be detected in the chemical composition of the oldest surviving stars. The first stars were brief, enormous, and transformative. They lit the universe and seeded it with the elements that everything else, every subsequent star, every planet, every living thing, would be built from. The birthplace of stars is the nebula, a vast cloud of gas and dust floating in the space between existing stars. These clouds, primarily composed of hydrogen gas with smaller amounts of helium and traces of heavier elements, can span hundreds of light years across and contain enough material to form thousands or even millions of stars. The process of star formation begins when a region within a nebula begins to collapse under its own gravity, triggered perhaps by the shockwave from a nearby supernova, or by the passage of a density wave through the galaxy. As the cloud collapses, it breaks into smaller fragments, each one contracting further, heating as the gravitational energy of infalling gas converts to heat. At the center of each collapsing fragment, a protostar forms, a dense, hot ball of gas that is not yet a true star, because it has not yet reached the temperatures needed to ignite nuclear fusion. The protostar continues to grow, accreting more gas from the surrounding cloud, heating further, drawing nearer to the moment of ignition. The nebula, in its quiet way, is the universe's nursery. Within its vast, cold, dark folds, the fires that will light the cosmos for billions of years are slowly, patiently gathering their strength. The moment that defines the birth of a true star, the transition from protostar to star, is the ignition of nuclear fusion in the core. This happens when the temperature at the center of the collapsing gas ball reaches approximately 10 million degrees Celsius, at which point hydrogen nuclei, protons, can overcome their mutual electrical repulsion and fuse together, forming helium nuclei and releasing enormous amounts of energy in the process. This energy release, the light and heat of nuclear fusion, creates an outward pressure that balances the inward pull of gravity. For the first time, the collapsing ball of gas reaches equilibrium. It is no longer falling inward. It is no longer just a cloud. It is a star. This balance between gravity pulling inward and the pressure of fusion energy pushing outward is called hydrostatic equilibrium, and it is the defining condition of a main sequence star. A star is, in its essence, a sustained negotiation between the force that wants to collapse everything into a point and the energy that pushes back against that collapse. For billions of years, that negotiation holds, and in holding, it makes light. Our own sun, the star that warms this planet, that drives the weather and the seasons and the life of everything on Earth, is approximately 4.6 billion years old. It formed from a collapsing cloud of gas and dust, like all stars, and it has been burning steadily in the heart of our solar system ever since. At 4.6 billion years of age, the Sun is approximately halfway through its expected lifespan. It will continue burning hydrogen in its core for another 5 billion years or so before its hydrogen supply runs low, and its behavior begins to change dramatically. 5 billion years is a number so large as to be essentially meaningless to human experience. In 5 billion years, every mountain on Earth will have eroded away and been rebuilt several times over. In 5 billion years, the continents will have drifted into configurations we cannot predict. In 5 billion years, life, if it persists, will be incomprehensibly different from what it is today. The Sun is not young, but it is not old. It is, cosmically speaking, in a long and stable middle age. Reliable, warm, still burning steadily, as it has burned every day of every life that has ever existed on Earth. At its most basic physical description, a star is a very large ball of plasma, a state of matter in which electrons have been stripped from their atoms by extreme heat, leaving a soup of free electrons and atomic nuclei. This plasma is held together by gravity and kept from collapsing by the energy of nuclear fusion in the core. The plasma of a star is not uniform. At the surface, where temperatures are lower, though still thousands of degrees, some atoms can exist in their normal bound state. In the deep interior, near the core, temperatures reach tens of millions of degrees, and all matter is fully ionized plasma. Despite its apparent solidity, the Sun looks like a solid, glowing ball from Earth. There is no solid surface anywhere in a star. From the outermost layers of the atmosphere, down through the visible surface, and deep into the interior, a star is entirely gas and plasma, different layers merging gradually into each other, rather than meeting at any sharp boundary. The composition of a typical star is remarkably simple. Approximately 73% of the Sun's mass is hydrogen, another 25% is helium. All other elements, oxygen, carbon, nitrogen, iron, gold, and everything else, together make up only about 2% of the total. This 2% of heavier elements is itself the product of stellar nucleosynthesis, the process by which nuclear fusion inside previous generations of stars created elements heavier than helium. In the very earliest stars, even this 2% did not exist. The universe began with only hydrogen and helium. Everything heavier was made inside stars. The extraordinary implication of this fact, which we will return to in more detail later, is that every atom of every element heavier than helium that exists in the universe, including every atom in your body, was forged inside the nuclear furnace of a star that lived and died before our own Sun was born. It is easy to think of the solar system as a collection of things: the Sun, the planets, the moons, the asteroids, the comets, roughly equivalent in their importance. But in terms of mass, the picture is staggeringly asymmetric. The Sun contains approximately 99.8% of all the mass in the entire solar system. All the planets, moons, asteroids, comets, and interplanetary dust together account for only 0.2%. Jupiter, the largest planet, a gas giant 11 times the diameter of Earth, accounts for more than half of that remaining 0.2%. Earth and all the other rocky planets together are a tiny fraction of of the solar system's total mass. The solar system is, in almost every meaningful physical sense, just the Sun, with a small amount of debris orbiting around it. A perspective that is hard to hold when standing on one of those small pieces of debris, feeling the ground solid beneath your feet. The temperature at the very center of the Sun, at the core where nuclear fusion occurs, is approximately 15 million degrees Celsius. At this temperature, hydrogen nuclei move fast enough to collide with sufficient energy to fuse, overcoming the electromagnetic repulsion between positively charged protons. This is an almost incomprehensible temperature. The surface of the Sun, by comparison, is approximately 5,500 degrees Celsius, still hot enough to vaporize any known material, but nearly 3,000 times cooler than the core. The energy produced by fusion in the core takes a very long time to reach the surface. Photons, particles of light, generated by fusion reactions in the core, are absorbed and re-emitted so many times as they travel outward through the dense solar interior that their journey from core to surface takes, on average, approximately 100,000 years. The light that left your window this morning was generated in the Sun's core roughly 100,000 years ago. By the time it finally escaped the solar surface, it crossed the 150 million kilometers of space to Earth in just over 8 minutes. The fundamental process that powers stars, nuclear fusion, is worth understanding in a little more depth because it is one of the most important processes in the universe. In the core of a main sequence star, hydrogen nuclei, protons, undergo a series of reactions collectively called the proton-proton chain, which ultimately converts 4 hydrogen nuclei into 1 helium nucleus. In this conversion, a small amount of mass is lost. The helium nucleus is very slightly less massive than the 4 protons that formed it. That small difference in mass is converted to energy, according to Einstein's famous equation, E equals mc squared. The speed of light squared is an enormous number, which means that even a tiny amount of mass converts to a very large amount of energy. Every second, the Sun converts approximately 600 million tons of hydrogen to helium. In the process, it loses about 4 million tons of mass, which becomes the energy that floods the solar system with light and heat. 4 million tons per second for 4.6 billion years, with approximately 5 billion more years to go. The scale of the Sun's energy production and the depth of its fuel reserves is one of the quietest and most fundamental facts about the world we inhabit. Among the most immediately striking things about the stellar universe is the extraordinary range of sizes that stars come in. Our Sun, which, from the perspective of daily life, seems enormous, is actually a rather average-sized star, and the range of star sizes extends so far above and below that average that the Sun, by comparison, begins to seem almost modest. At the small end of the scale, red dwarf stars, the most common type of star in the galaxy, can be as small as 1/10 the diameter of the Sun. They are so dim that none are visible to the naked eye from Earth, despite some being our nearest stellar neighbours. At the large end of the scale, hypergiant stars can reach diameters of 1,000 times the Sun or more. If the Sun were replaced by the hypergiant star UY Scuti, currently considered among the largest known stars, its surface would extend beyond the orbit of Jupiter. The entire inner solar system, including Earth, would be subsumed within the star. The universe makes stars in sizes that range from smaller than a planet to larger than the orbit of Jupiter. It does not specialize. Look carefully at a clear night sky, and you will notice that not all stars are the same color. Some appear white. Some have a warm, slightly orange or reddish tint. Some, with attention, can be seen to have a faint blue or blue-white hue. These differences in color are not optical illusions. They are real, and they tell us something important about each star. The color of a star is determined by its surface temperature. The coolest stars, with surface temperatures around 3,000 degrees Celsius, emit mostly red and orange light, and appear red or orange-red. Stars at intermediate temperatures, like our Sun, emit light centered in the yellow-green part of the spectrum and appear yellowish-white. The hottest stars, with surface temperatures above 25,000 degrees, emit predominantly blue and ultraviolet light and appear blue-white. When you look at the night sky with this knowledge, it becomes a kind of temperature map. The cool red stars, warm yellow stars, and blazing blue-white ones spread across the dome of the sky, each one broadcasting its temperature through the color of its light across tens or hundreds of light years of space. Astronomers classify stars according to their spectral type, a classification based on the pattern of absorption lines in the star's light, which reflects the star's temperature and chemical composition. The main spectral classes, from hottest to coolest, are designated by the letters O, B, A, F, G, K, and M, often remembered through the mnemonic, "Oh, be a fine girl/guy, kiss me." Our Sun is a G-type star, a yellow dwarf with a surface temperature of about 5,500 degrees and a characteristic pattern of absorption lines. The hot, blue-white stars of the O and B classes are the rarest and most short-lived. The cool red M-type stars are the most common, accounting for perhaps 70% of all stars in the galaxy. This classification system, which emerged from the patient spectroscopic work of astronomers in the late 19th and early 20th centuries, transformed our understanding of stars from points of light into physically understood objects. Each one's temperature, age, mass, and eventual fate readable with the right tools in the character of its light. This sounds obvious, but it is worth pausing on. The Sun is a star. The nearest star in the universe to the planet Earth is not some distant point of light in the night sky. It is the blazing object that defines our day, that drives our seasons, that has sustained life on Earth for 4 billion years. The Sun is so close that its light takes only 8 minutes and 20 seconds to reach us. The next nearest star, Proxima Centauri, a red dwarf in the Alpha Centauri system, is approximately 4.24 light-years away. Light traveling at 300,000 kilometers per second would take more than 4 years to bridge that distance. Every star in the night sky is enormously farther away than the Sun. The apparent similarity between the Sun and the distant stars, both appear as light sources from Earth's surface, belies the extraordinary difference in distance. The Sun is our star, close and intimate. The rest are remote and ancient, their light arriving after journeys of years, decades, centuries, and millennia. When you look at the night sky, you are not seeing the stars as they are now. You are seeing them as they were when the light that is currently entering your eyes left their surfaces. And because stars are so far away, that light may have been traveling for a very long time. The stars in the Big Dipper, a familiar northern constellation, are between 60 and 120 light-years away. The light currently reaching your eyes from those stars left them sometime between the American Civil War and the Middle Ages. The Andromeda Galaxy, visible to the naked eye on clear nights, is 2.5 million light-years away. The light reaching us from Andromeda left it when our ancestors were making stone tools in the African savanna. The night sky is not a picture of the universe as it is. It is a picture of the universe as it was, a mosaic of different moments in time, each point of light a window into a different past. Looking up at the stars is looking back through time. The sky above you on any clear night is a kind of history written in light. Of all the properties of a star, the single most important is its mass. A star's mass determines how hot its core burns, how bright it shines, how long it lives, how it dies, and what it leaves behind. Mass is the fundamental parameter from which almost everything else about a star's life follows. Massive stars burn hotter and brighter than low-mass stars because their greater gravity requires more fusion energy to maintain hydrostatic equilibrium. But this greater brightness comes at a cost. Massive stars burn through their hydrogen fuel far more rapidly and have correspondingly shorter lifespans. A star 10 times the mass of the Sun will be tens of thousands of times more luminous and will exhaust its hydrogen in only a few tens of millions of years. A star half the mass of the Sun will burn dimly but patiently for trillions of years, far longer than the current age of the universe. The universe's most massive stars live like brilliant, brief flames. Its least massive stars are patient, dim, and essentially eternal by any human measure. Our Sun's total main sequence lifespan, the time it will spend burning hydrogen in its core, is estimated at approximately 10 billion years. Having already burned for 4.6 billion years, it is, as we noted earlier, roughly halfway through. The remaining 5 billion years of the Sun's main sequence life represent an almost incomprehensible period of stability. For 5 billion more years, the Sun will rise each morning, set each evening, warm the surface of a changing Earth, and fuel whatever life persists here. Its output will increase very slowly over this time. It is currently about 30% brighter than when it first formed. But the changes will be gradual, almost beyond perception on any human timescale. This stability, this reliable, enduring, patient burning, is one of the preconditions for the development of complex life on Earth. Life needed billions of years to evolve to its present complexity, and it had them because the Sun provided a reliable energy source across all that time without dramatic variation. The Sun's steady burning is the quiet foundation beneath everything. Astronomers use a diagram called the Hertzsprung-Russell diagram, or HR diagram, to map the properties of stars. When the luminosity of a star is plotted against its temperature, most stars fall along a diagonal band running from the upper left, hot and bright, to the lower right, cool and dim. This band is called the main sequence, and it represents stars that are burning hydrogen in their cores. A star spends the vast majority of its entire lifespan on the main sequence. For the Sun, that is 10 billion years of relatively stable hydrogen burning. The more dramatic phases, the red giant phase, the death event, the remnant, are brief by comparison, though they are often the most spectacular. The main sequence is the long, quiet life of a star, the settled, stable middle existence between birth and the more dramatic events that bookend it. It is a useful metaphor, perhaps, for the long settled periods of any existence, the years that feel ordinary and unremarkable, but which constitute, in total, most of what there is. The central conflict of every star's life, the tension that will eventually end the long stability of the main sequence, is the slow depletion of hydrogen fuel in the core. Over billions of years, the hydrogen at the center of the star is converted to helium. Slowly, the core becomes increasingly helium-rich, and the rate of fusion in the core changes. When the hydrogen in the core is finally exhausted, fusion ceases at the center. Without the outward pressure of fusion energy, gravity begins to win the long negotiation, and the core starts to contract. This contraction releases gravitational energy as heat, which causes the outer layers of the star to expand dramatically. The star swells. This is the beginning of the end of the main sequence, the first step in the complex and often spectacular sequence of events that will eventually lead to the star's death. The depletion of core hydrogen is a slow, invisible, irreversible process, proceeding over billions of years without any outward sign. And then, eventually, the balance shifts and the star begins to change. For a star like our Sun, a middle mass star, the exhaustion of core hydrogen leads to a dramatic expansion into what is called a red giant. As the core contracts and heats, hydrogen fusion begins in a shell around the core, generating enormous energy that causes the outer layers of the star to swell outward to hundreds of times the star's original diameter. As the outer layers expand and cool, the star's surface temperature drops and its color shifts toward red, giving the red giant phase its name. Our Sun will eventually expand to approximately 200 times its current diameter, large enough to swallow Mercury and Venus, and to extend almost to Earth's current orbit. The red giant phase lasts for roughly 1 to 2 billion years. During this time, the core continues to contract and heat until it reaches temperatures sufficient for helium fusion to begin, creating carbon and oxygen. Then, eventually, the helium in the core is also exhausted, and the star's path leads to its final act. Despite the fact that no red dwarf is visible to the naked eye from Earth, these small, cool, dim stars are by far the most numerous type of star in the Milky Way galaxy. Estimates suggest that red dwarf stars, M-type stars with masses between about 8 and 60% of the Sun's mass, may account for 70 to 80% of all stars in the galaxy. Their abundance reflects the way star formation works. It is much more common for a collapsing gas cloud to produce a small, low-mass star than a massive one. The most massive stars are rare precisely because the conditions needed to produce them, very dense, very large collapsing regions, are uncommon. Red dwarfs burn so slowly and so dimly that their hydrogen fuel will last for tens to hundreds of billions of years. In a universe that is currently only 13.8 billion years old, no red dwarf has yet had time to exhaust its fuel. Every red dwarf that has ever formed is still burning. They will outlast everything else in the stellar universe by an enormous margin. Patient, dim, and effectively eternal. Stellar pulsation is a phenomenon where stars expand and contract rhythmically, becoming brighter when they compress and dimmer when they expand. Cepheid variables are yellow giant and supergiant stars with pulsation periods from days to weeks. Their pulsation period is directly related to their intrinsic brightness, allowing astronomers to determine their distance by comparing real and observed brightness. This relationship discovered in 1908, provided the first reliable way to measure distances to other galaxies and helped establish that distant nebulae are separate galaxies beyond the Milky Way. When we think of a star, we typically imagine a single sun, a lone sphere of plasma in otherwise empty space. But this is not the most common arrangement. Many stars, estimates range from about half to more than 2/3 of all stars, exist in binary or multiple star systems, two or more stars bound together by mutual gravity, orbiting a common center of mass. Binary stars can be separated by enormous distances, taking thousands of years to complete a single orbit around each other. Or they can be so close that they are nearly touching, tidally distorted by each other's gravity, occasionally even exchanging mass, their mutual influence shaping the evolution of both stars in ways that would not occur for isolated stars. Our own sun is, apparently, a relatively unusual loner. Many of the stars in the night sky are double stars, what appears to be a single point of light, being in reality two stars so close together that only a telescope can separate them. The night sky is more populated than it appears. As a star ages and its surface temperature changes, whether through the main sequence evolution as its luminosity slowly increases, or through the dramatic changes of the red giant phase, its color shifts accordingly. A star that was born blue-white will gradually become yellower and then cooler as it ages on the main sequence. As it expands into a red giant, its surface cools further, and its color shifts toward orange and then red. These color shifts are so slow on human timescales as to be completely imperceptible. No person or even any civilization will ever witness the color of the sun changing. But across millions and billions of years, the color of a star tells the story of its aging, a slow, luminous autobiography written in light. For most of history, it was unknown whether stars had planets because planets are faint and difficult to detect near bright stars. The first confirmed exoplanet around a sun-like star was discovered in 1995. Since then, thousands of exoplanets have been found using methods like the transit method and radial velocity. As of the mid-2020s, over 5,000 exoplanets have been confirmed, with many more candidates. Evidence suggests that planets are very common and that Earth-like planets in habitable zones may be widespread across the galaxy. As with so much else in stellar life, a star's death is determined primarily by its mass. The death of a low-mass star, a medium-mass star, like the Sun, and a massive star are three very different events, different in their timescales, their drama, their energy release, and in what they leave behind. Low-mass stars, those below about half the mass of the Sun, will eventually settle into a long, slow dimming, burning their hydrogen fuel entirely and cooling gradually into cold, dark balls of degenerate matter called black dwarfs. But because their lifespans are so long, trillions of years, no black dwarf has yet had time to form in the current universe. Medium-mass stars, like the Sun, end in the gentler drama of the planetary nebula and white dwarf. Massive stars end in the spectacular violence of a supernova, an explosion that can briefly outshine an entire galaxy, leaving behind either a neutron star or a black hole. Each of these paths is extraordinary in its own way. Each one is a story of what happens when the long negotiation between gravity and fusion energy finally reaches its end. When a star like the Sun reaches the end of its red giant phase, it does not explode. Instead, it sheds its outer layers in a slow, expanding shell of gas that drifts outward into surrounding space. This expanding shell, illuminated by the hot core that remains behind, is called a planetary nebula, a name chosen by early astronomers who thought the rounded, glowing shapes resembled the disk of a planet through a telescope. The expanding gas disperses over roughly 10,000 years, enriching the interstellar medium with elements like carbon and oxygen, which become the raw material for future stars, planets, and, where conditions permit, future life. At the center of a planetary nebula, after the outer layers have been shed, the collapsed core of the dead star remains. This remnant, called a white dwarf, is an extraordinary object. It contains roughly the mass of the original Sun, compressed into a sphere approximately the size of Earth. The density of a white dwarf is extreme. A teaspoon of white dwarf material would weigh approximately 5 tons on Earth. The white dwarf is not supported by fusion energy. There is no more fusion occurring, but by a quantum mechanical effect called electron degeneracy pressure, in which the laws of quantum physics prevent the electrons in the compressed material from being packed any more closely together. A newly formed white dwarf is extremely hot, tens of thousands of degrees, and shines brightly in ultraviolet light. Over billions of years, it will cool and fade, eventually becoming a cold, dark, invisible ball of degenerate matter, a black dwarf. But this cooling takes far longer than the current age of the universe, so every white dwarf that has ever formed is still glowing somewhere in the galaxy. For stars above approximately 8 times the mass of the Sun, the end is not the gentle exhalation of a planetary nebula, but one of the most violent events in the universe, a core collapse supernova. When a massive star exhausts the fuel in its core, the core collapses in a fraction of a second, an almost instantaneous implosion from the size of Earth to a sphere just a few kilometers across. The gravitational energy released is so enormous that it blows the outer layers into space in a cataclysmic explosion, briefly making the star as bright as an entire galaxy. A supernova can be visible in daylight from Earth. When one occurred in the Large Magellanic Cloud in 1987, it was visible to the naked eye for months and released, in seconds, more energy than the Sun will emit in its entire lifetime. The expanding shockwave from a supernova spreads through space for thousands of years, compressing nearby gas clouds and sometimes triggering the formation of new stars. The death of one star can plant the seeds of many others. Among the most profound things a supernova does is create and distribute elements. The extreme temperatures and pressures of a supernova drive nuclear reactions that create many of the heaviest elements in the periodic table, including gold, platinum, silver, and uranium. These elements, along with those formed during the star's life, are scattered into space and mix with the interstellar medium, becoming material for future stars and planets. Every gold ring and silver spoon and other such materials contain elements created in the death of massive stars billions of years ago, later assembled by gravity into new systems, planets, and eventually life. When the most massive cores collapse in a supernova, the remnant left behind is an object even stranger than a white dwarf, a neutron star. A neutron star forms when the collapsing core becomes so dense that electron degeneracy pressure can no longer resist gravity, and electrons and protons combine to form neutrons, creating an object supported by neutron degeneracy pressure. A typical neutron star contains about 1.4 times the mass of the Sun, compressed into a sphere only about 20 kilometers across. Its density is extreme, and its surface gravity is so strong that falling matter would reach a significant fraction of the speed of light before impact. Neutron stars spin very rapidly, and many emit beams of radio waves from their magnetic poles. When these beams sweep past Earth, they are detected as regular pulses of radio emission. These objects, called pulsars, keep time more precisely than any human-made clock. When the collapsing core of a very massive star exceeds approximately 3 solar masses, even neutron degeneracy pressure cannot resist gravity, and the core collapses to a singularity surrounded by a region from which not even light can escape, a black hole. The boundary from which nothing can return is called the event horizon. Once something crosses it, no signal can escape to the outside universe. Black holes are invisible, but can be detected by their gravitational effects on nearby matter, by X-ray emission from infalling gas, and by the gravitational waves produced during mergers with other black holes or neutron stars. What happens at the singularity, the point of infinite density, is unknown and remains one of the deepest open problems in science. Not all supernovae involve the core collapse of a massive star. A second type, called a Type 1a supernova, occurs when a white dwarf in a binary system accretes enough mass from a companion star to exceed a critical mass threshold called the Chandrasekhar limit, approximately 1.4 solar masses. When this limit is exceeded, carbon fusion ignites suddenly throughout the white dwarf, which explodes completely, leaving no remnant at all. Type 1. A supernovae are remarkable for their consistency, because they all occur at nearly the same mass and energy. They all reach approximately the same maximum brightness. This consistency makes them reliable standard candles. Objects of known intrinsic brightness that allow astronomers to measure distances across cosmological scales by comparing apparent brightness to known true brightness. It was through measurements of Type 1a supernovae that astronomers discovered in 1998 that the expansion of the universe is accelerating, a discovery that implied the existence of a mysterious dark energy driving the universe apart, and that earned the 2011 Nobel Prize in Physics. The quiet death of distant white dwarfs, billions of light years away, revealed the deepest fact about the large-scale fate of the universe. Among the most famous stars in the night sky is Betelgeuse, the bright reddish-orange star that marks the right shoulder of the constellation Orion. It is a red supergiant, one of the largest and most luminous stars visible to the naked eye, located about 700 light-years from Earth. If it replaced the Sun, its surface would extend beyond the orbit of Jupiter. It is burning through its fuel at a high rate and is expected to end in a supernova within the next 100,000 years. When it does, it will be briefly visible in daylight from Earth. Betelgeuse shows that the night sky is not static. The stars we see today will not be the same for future generations, as the sky slowly changes over time. The brightest star in the night sky is Sirius, the main star of the constellation, Canis Major. It is about 8.6 light-years from Earth, roughly twice the mass of the Sun, and 25 times more luminous, which explains its brightness. Sirius has been important in many cultures. In ancient Egypt, its rising before dawn coincided with the annual flooding of the Nile, and the calendar was based on this cycle. The name Sirius comes from the Greek for glowing. On clear nights, Sirius appears to twinkle near the horizon, showing shifting colours due to Earth's atmosphere. This effect comes from atmospheric refraction, not from the star itself, which shines steadily. A common misconception is that Polaris, the North Star, the star directly above Earth's North Pole, is the brightest star in the night sky. In fact, Polaris is a relatively modest star in terms of brightness, ranked only about 49th brightest among stars visible from Earth. Polaris's importance is entirely positional. It happens to lie almost directly above Earth's geographic North Pole, within less than 1 degree of the celestial North Pole, which means that as Earth rotates, all other stars appear to circle around Polaris. It alone appears to stay fixed in the sky, making it an invaluable navigational reference for anyone in the Northern Hemisphere. This positional coincidence is, in cosmic terms, temporary. Earth's axis wobbles slowly in a circle, a motion called precession, with a period of approximately 26,000 years. Over this precession cycle, different stars serve as the North Star. About 13,000 years from now, the bright star Vega will be near the celestial North Pole, and future navigators will use it as their guiding star. Among the contenders for the title of largest known star is VY Canis Majoris, a red hypergiant located approximately 3,900 light-years from Earth in the constellation Canis Major. Its radius is estimated at around 1,400 to 2,000 times the radius of the Sun. If VY Canis Majoris were placed at the center of our solar system, its surface would extend past the orbit of Saturn. A beam of light traveling around its equator at 300,000 kilometers per second would take approximately 8 hours to complete one circuit. To fly around it in a commercial aircraft would take approximately 1,100 years. VY Canis Majoris is so massive and so luminous that it is slowly destroying itself, losing mass at a prodigious rate through powerful stellar winds, shedding enormous amounts of material into the surrounding space. It is, by most measures, near the end of its life, and expected to explode as a hypernova in the relatively near astronomical future. The nearest star to our solar system, other than the Sun itself, is Proxima Centauri, a small red dwarf located approximately 4.24 light-years away in the southern constellation Centaurus. Despite being our nearest stellar neighbor, Proxima Centauri is far too dim to see with the naked eye. In 2016, astronomers announced the discovery of a planet, Proxima Centauri b, orbiting within the habitable zone of Proxima Centauri. This planet, approximately the size of Earth, is the nearest known exoplanet to the solar system. Whether Proxima Centauri b could support life is unknown and perhaps unlikely. Proxima Centauri is a flare star that periodically blasts its surroundings with intense radiation, which may sterilize any planet's surface. But its existence, so close to home, in the habitable zone of its star, is a quiet reminder that the nearest other world may be much closer than we tend to assume. Deep in the southern constellation, Carina, at a distance of approximately 7,500 light-years, Eta Carinae is one of the most extreme stars in the Milky Way. It is a stellar binary system, two massive stars orbiting very closely together, with a combined mass estimated at 100 to 170 solar masses, and a luminosity 5 million times that of the Sun. In the 1840s, Eta Carinae underwent a dramatic brightening, an event called the Great Eruption, in which it briefly became the second brightest star in the sky, despite its great distance, before fading back to invisibility to the naked eye. The material ejected during this eruption formed the homunculus nebula, a pair of expanding lobes of gas and dust visible around the star today. Eta Carinae is considered a strong candidate for one of the next supernovae visible from Earth, though next, in astronomical terms, could mean anywhere from tomorrow to several thousand years from now. When it goes, it will be spectacular. Our Sun, the star at the center of our solar system, 8 minutes of light away, is one of approximately 200 to 400 billion stars in the Milky Way galaxy. It lies about 26,000 light-years from the galactic center, in a relatively quiet region of a spiral arm. The Milky Way is a barred spiral galaxy, a flattened disk of stars, gas, and dust, with a central bar and spiral arms. From Earth, we see it as a faint band of light across the night sky, made up of billions of distant stars. The Sun completes one orbit around the galactic center in about 225 million years, a period called a galactic year. Over its 4.6 billion year lifetime, it has completed roughly 20 orbits around the Milky Way. Long before the invention of the compass or maps, humans navigated by stars. Identifying constellations and using their positions for direction and seasonal timing was developed independently by cultures worldwide and enabled important journeys in human history. Polynesian navigators used stars, ocean currents, and wave patterns to cross the Pacific Ocean and settle islands across vast distances with high accuracy. For them, the stars served as navigation paths. In the modern age of GPS, this close familiarity with the night sky has largely faded, but the stars that once guided ancient travelers are still present and visible on clear nights. The ancient Egyptians incorporated stellar alignments into the construction of their most important monuments. The Great Pyramid of Giza, built approximately 4,500 years ago, is oriented with extraordinary precision to the cardinal directions, and its internal shafts are aligned to the positions of specific stars as they appeared in the Egyptian sky at the time of construction. One shaft in the King's Chamber of the Great Pyramid points toward Orion's belt, associated by the Egyptians with the god Osiris. Another points toward the star Thuban, which was the pole star at the time of the pyramid's construction. These alignments were not accidental. They reflect a sophisticated knowledge of astronomy, integrated with religious and ceremonial significance. Many other ancient monuments across many cultures show similar astronomical alignments. Stonehenge, Newgrange, the temples of Angkor Wat, the layouts of Mesoamerican cities. The stars were not merely objects of curiosity to these cultures. They were the framework within which human life, religion, and time itself were understood. The constellations we recognize today, Orion, the Big Dipper, Scorpius, the Southern Cross, are patterns created by human perception, not physical groupings of nearby stars. The stars of Orion's belt lie at different distances from Earth and have no real physical connection. Their alignment is a coincidence of perspective. Different cultures have interpreted the same stars in different ways, giving them different meanings and figures. For example, Orion was seen as various figures across cultures, and the Southern Cross was not recognized by European astronomers until later exploration. The Greek astronomer Hipparchus, working in the 2nd century BCE, compiled what is considered the first systematic catalogue of stars, recording the positions and brightness of approximately 850 stars with unprecedented accuracy for his time. He also developed the system of stellar magnitudes, measuring the apparent brightness of stars on a numerical scale. That, in modified form, astronomers still use today. Hipparchus also discovered the precession of the equinoxes, the slow wobble of Earth's axis that causes the celestial pole to describe a circle among the stars over 26,000 years. By comparing his observations with those of earlier Babylonian astronomers. This was a discovery of extraordinary subtlety, requiring careful, long-term measurements and a mind capable of detecting a pattern in data separated by generations. The patient, careful, observation-based approach that Hipparchus applied to the night sky, recording what he saw, comparing it to what others had seen before him, inferring from those comparisons a deeper truth about the structure of the cosmos, is the same fundamental approach that astronomy still uses 2,000 years later with vastly better instruments. In 1814, the German optician Joseph von Fraunhofer discovered that sunlight passed through a prism produces a spectrum with dark lines caused by light absorbed by atoms in the solar atmosphere. These absorption lines, called Fraunhofer lines, act like a fingerprint. Each chemical element absorbs light at specific wavelengths, allowing astronomers to identify elements, their proportions, and temperature in stars. Spectroscopy transformed astronomy into a science of composition, making it possible to determine that stars contain the same elements found on Earth, even at great distances. The universe, spectroscopy revealed, is made of the same ingredients everywhere. Chemistry is universal. Every atom in your body, except hydrogen, which was formed in the Big Bang, was forged inside stars. Carbon in DNA, oxygen in water, and iron in hemoglobin were created in stellar processes and in the final stages of massive stars before supernova explosions. These atoms were scattered into space, traveled through the interstellar medium, and were eventually gathered by gravity to form the Sun, the Earth, and life. You are made of stardust. This is not a metaphor. It is chemistry. The Sun is the ultimate energy source for life on Earth. Through photosynthesis, plants and other organisms capture sunlight and convert carbon dioxide and water into organic molecules, the basis of all living things. The energy in all food ultimately comes from sunlight. Whether from plants or from animals that eat plants, every calorie traces back to energy that traveled from the sun. Solar energy also drives the water cycle, weather, atmospheric circulation, and the formation of fossil fuels over millions of years. Civilization, food, and warmth all depend on the sun's ongoing nuclear fusion. The universe began with hydrogen and helium, with trace lithium. All heavier elements were formed later through stellar nucleosynthesis inside stars and during supernova. Without stars, the universe would lack chemical complexity. No water, no carbon, no DNA, and no life. Stars act as the universe's chemical factories, producing all elements heavier than helium. The diversity of elements and molecules, including those essential for life, comes from generations of stars that existed before our solar system. The planet Earth is rich in heavy elements like iron and nickel, which were formed in massive stars before the Sun existed. Isotopic analysis of meteorites and Earth rocks shows evidence of this stellar nucleosynthesis, reflecting processes that occurred in ancient stars and supernovae billions of years ago. Some of these elements were likely incorporated into the solar nebula from nearby supernova ejecta shortly before the Sun formed. possibly even triggering its formation. Earth, in this sense, is a product of earlier stellar explosions, formed from their remnants and enriched by their elements. In about 5 billion years, the Sun will expand into a red giant, likely engulfing the inner planets. Earth may be destroyed or rendered uninhabitable by intense radiation. Oceans will boil, the atmosphere stripped, and the surface scorched. Any life remaining will face conditions it cannot survive. This event is far in the future, longer than Earth's current age and the entire span of life's evolution. So, it is not an immediate concern. The Sun's eventual expansion is simply the final chapter in a very long, slow, patient story. And tonight, with 5 billion years still in the account, we can rest easy. One of the most cited facts in all of popular astronomy, one that never entirely loses its power to humble, is the comparison between the number of stars in the observable universe and the number of grains of sand on all of Earth's beaches. The observable universe contains an estimated 2 trillion galaxies, each containing on average hundreds of billions of stars. The total number of stars in the observable universe is estimated at roughly 1 septillion, that is, 1 followed by 24 zeros, or 10 to the 24th power stars. The estimated number of sand grains on all of Earth's beaches and deserts combined is approximately 10 to the power of 19, 10 million billion. There are approximately 100,000 stars in the observable universe for every grain of sand on Earth's beaches. This comparison does not diminish the sand, which is beautiful and sufficient in its own right. It simply places the scale of the stellar universe in a context that the human mind can, briefly and imperfectly, begin to feel. We are small creatures on a small planet, orbiting one star among more stars than there are grains of sand on our beaches. And we have looked up, and we have wondered, and we have understood. That, perhaps, is the most remarkable thing of all. Our home galaxy, the Milky Way, contains an estimated 200 to 400 billion stars, a number so large that if you were to count one star per second, it would take over 6,000 years to count them all. These stars are distributed in a disk approximately 100,000 light-years across and a few thousand light-years thick, with a central bulge and several spiral arms extending outward from the center. The Milky Way also contains enormous quantities of gas and dust, the raw material for future generations of stars, as well as dark matter, whose gravitational effects shape the galaxy's structure, but whose nature remains mysterious. From the inside, we can only see a relatively small portion of the galaxy. Dust in the plane of the disk obscures our view across most of the galactic disk. The comprehensive picture of our galaxy's structure has been assembled by astronomers using radio telescopes, infrared telescopes, and other instruments that can peer through the obscuring dust. The shape of our own home is something we have had to infer indirectly, looking at the galaxy from within it like a person trying to describe the room they are sitting in while blindfolded. Astronomers classify stars in the Milky Way by their chemical composition into 3 populations based on their metal content, elements heavier than helium. Population 1 stars, like the Sun, are metal-rich and formed from gas enriched by previous stellar generations. Population 2 stars are older and metal-poor, formed when the galaxy was younger. Population 3 stars are the first generation, composed only of hydrogen and helium, and have not yet been observed. These populations trace the galaxy's history. The oldest stars formed over 13 billion years ago, while younger stars form from gas enriched by earlier stars. The Sun is a second or third generation star, formed 4.6 billion years ago. Its existence, and that of Earth and life, depends on earlier generations of stars. In approximately 4 to 5 billion years, the Milky Way and the Andromeda Galaxy, the large spiral galaxy visible to the naked eye on clear dark nights in the Northern Hemisphere, will collide and merge into a single, larger elliptical galaxy. Collision is perhaps a misleading word. The galaxies themselves are mostly empty space. The actual stars within each galaxy will almost certainly not collide. They will pass by each other, like two swarms of fireflies interpenetrating in the dark. But the gravitational interaction between the two galaxies will dramatically reshape both, distorting their spiral structures, triggering waves of new star formation, and eventually settling into a merged system. This future collision will not destroy the solar system, and by the time it occurs, 4 to 5 billion years from now, the Sun will be well into its red giant phase anyway. The Great Galactic Merger and the expansion of the Sun will be, in cosmic timing, nearly simultaneous events. The universe works on its own schedule, enormous, slow, and patient. Just as planets orbit the Sun, stars in the Milky Way orbit the galaxy's center, which is dominated by the supermassive black hole Sagittarius, a star with a mass of about 4 million solar masses. The Sun moves at about 828,000 kilometers per hour and completes one orbit roughly every 225 million years. Despite this speed, the galaxy's immense scale makes this motion appear extremely slow over human lifetimes. So the galaxy seems almost static, even though all stars are in motion. Over thousands of years, stars gradually shift position. Constellations change over time and will become unrecognizable in about 100,000 years as stars follow their own paths through the galaxy. Among the various types of neutron stars, one group is particularly extreme: magnetars. These objects have magnetic fields so intense that they are approximately 1 trillion times stronger than the strongest magnetic field ever produced by human technology on Earth. A magnetar's magnetic field is so powerful that, from a distance of several 100,000 kilometers, it would disrupt the electrons within the atoms of your body. A reminder of the vast scales of force that exist in the stellar universe. Magnetars occasionally undergo sudden magnetic field reconfigurations, starquakes, that release enormous bursts of gamma rays and X-rays. A magnetar flare detected in December 2004 from a source about 50,000 light-years away briefly ionized Earth's upper atmosphere, even at that extreme distance, momentarily altering the electrical properties of the sky above us, sent from a star half the galaxy away. The most rapidly rotating known neutron stars, millisecond pulsars, can complete hundreds of full rotations per second. The current record holder rotates approximately 716 times per second, meaning its equatorial surface is moving at a significant fraction of the speed of light. This extraordinary rotation is the result of conservation of angular momentum. When the massive core of a dying star collapses to a tiny neutron star, the reduction in size, like a spinning ice skater pulling in their arms, causes the rotation rate to increase enormously. The Sun rotates roughly once per month. Its collapsed remnant would rotate hundreds of times per second. The surface of a millisecond pulsar is a place of almost unimaginable physical extremes. Crushing gravity, intense magnetic fields, intense radiation, and a surface racing around its axis at a significant fraction of the speed of light. It is one of the most extreme environments the universe contains, and it was once the core of a star not entirely unlike our own. When two stars in a binary system are close enough, the gravity of one can pull material from the other, a process called mass transfer. This exchange of material can have dramatic effects on both stars' evolution, causing the accreting star to grow and change, while the donor star is gradually depleted. In some systems, mass transfer onto a white dwarf builds up until it triggers a thermonuclear explosion on the white dwarf surface, a nova. Unlike a supernova, a nova does not destroy the star. After the explosion, the mass transfer resumes, and the cycle may repeat. Novae on the same star observed multiple times over human historical periods. The complex gravitational dance of binary stars, two fires orbiting each other, slowly exchanging their substance, each affecting the other's fate, is one of the more intricate stories the stellar universe tells. Star formation is not a thing of the past. New stars are forming throughout the universe right now, in dense molecular clouds in the Milky Way, in the arms of other spiral galaxies, in the turbulent gas of interacting galaxies. The Orion Nebula, visible to the naked eye as the fuzzy middle star in Orion's sword, is an active star-forming region about 1,300 light-years away, where new stars are being born as you read this. The rate of star formation in the universe was much higher in the past. The cosmic star formation rate peaked approximately 10 billion years ago and has been declining since, but it has not stopped. The universe continues, quietly and continuously, to make new stars. Among the stars forming in the universe tonight, some will be long-lived red dwarfs that will burn for trillions of years. Some will be short-lived massive stars that will explode within millions of years. Perhaps some of them will eventually have planets. Perhaps some of those planets will eventually have something that wonders about the stars above it. The overwhelming majority of the visible light in the observable universe is produced by stars. Galaxies shine because of their stars. The faint background glow of the universe, the accumulated light of all the stars that have ever shined, is a testament to the productivity of stellar fusion across 13 billion years of cosmic history. When astronomers look at the oldest, most distant galaxies, seen as they were only a few 100 million years after the Big Bang, they see the intense blue glow of young, hot, massive stars in the first episodes of vigorous star formation. The universe went from darkness to blazing with light in just a few 100 million years, as the first stars and galaxies ignited. The light that fills the universe, from the glow of nearby nebulae to the faint signatures of the most distant galaxies, is, at its source, the light of nuclear fusion. Hydrogen converted to helium, mass converted to energy, the universe illuminating itself through the patient chemistry of its own stars. While the hottest stars that are still burning hydrogen, the O-type blue giants and hypergiants, have surface temperatures of around 50,000 degrees. Some stellar remnants are even hotter. The central stars of planetary nebulae, the exposed cores of dying stars still contracting toward white dwarfs, can reach surface temperatures of over 200,000 degrees Celsius. At these temperatures, the star emits primarily in the extreme ultraviolet and X-ray portions of the spectrum. Radiation invisible to human eyes and absorbed by Earth's atmosphere, but detectable by space-based telescopes. These hot, pre-white dwarfs illuminate the nebulae surrounding them, causing the gas to fluoresce in the beautiful colors captured in images of planetary nebulae. The hottest stellar surfaces are not the surfaces of the most luminous stars currently burning, but the exposed cores of stars that have shed their outer layers. Stellar remnants still radiating the heat of a lifetime of nuclear burning. At the other extreme, the coolest stars blur the boundary between stars and planets. Brown dwarfs, objects too small to sustain hydrogen fusion, but too large to be considered planets, span the gap between the least massive stars and the most massive gas giant planets. The coolest brown dwarfs have surface temperatures below 1000 degrees Celsius, cooler than some chemical reactions and barely warmer than the filament of a conventional light bulb. Below about 1300 degrees, brown dwarfs can even host clouds in their atmospheres. Clouds not of water vapor, but of iron droplets, silicate particles, and other exotic materials that condense at these extreme but relatively cool stellar temperatures. These cool, faint, cloud-wrapped objects are barely stars at all. They bridge the gap between the blazing nuclear furnaces above them and the cold, dark planets below. They glow faintly in the infrared, invisible to the unaided eye, orbiting in the dim regions of the galaxy where few would notice them. HD 140283, a star located about 190 light-years from Earth in the constellation Libra, has been estimated to be approximately 14.5 billion years old, making it potentially older than current estimates for the age of the universe itself, 13.8 billion years. This apparent paradox has generated significant discussion among astronomers, and most believe the discrepancy reflects uncertainties in the age measurements rather than a true violation of physics. Nonetheless, HD 140283, sometimes called the Methuselah star, is undeniably ancient. Its extreme metal pore composition places it firmly among the first generations of stars to form in the Milky Way, from gas that had been only slightly enriched by the first supernovae. This star was already old when the Sun formed. It was already old when Earth's first oceans pooled in the ancient craters of the cooling rock. It has been burning quietly, dim and patient, in our stellar neighborhood for longer than almost anything else in the local universe. It is, in some ways, the closest thing in the sky to a beginning. The most massive stars push against fundamental physical limits. Above a certain mass, roughly 150 to 200 solar masses, a star becomes so luminous that its own radiation pressure can exceed the gravitational force holding it together. Such stars are inherently unstable, losing mass rapidly through violent stellar winds and episodic eruptions. Despite this instability, stars of approximately 150 to 300 solar masses are believed to exist, at least briefly, in the most active star-forming regions. R13601, a star in the Large Magellanic Cloud, has been estimated at roughly 265 solar masses, though even this figure carries significant uncertainty. Such stars live only a few million years before exploding in the most powerful supernovae, or hypernovae, the universe can produce. These extreme objects represent the universe testing the outer boundaries of what a star can be. Where physics permits a thing to exist, the universe eventually produces it. if only briefly, if only at the edge of what is stable, if only for a cosmic moment before the inevitable collapse. Most stars are found within galaxies, but some, called intracluster or intergalactic stars, drift in the space between galaxies after being ejected by gravitational interactions. These isolated stars travel through regions where nearby stars are hundreds of thousands of light years away, making intergalactic space far emptier than interstellar space. Their planets, if they exist, would have nearly starless night skies, with only faint, distant galaxies visible. A planet orbiting such a star would be one of the most isolated places in the universe, surrounded by vast darkness and illuminated only by its single star. Across the full breadth of human history and geography, every culture that has left records has named the stars and found patterns in them. The Babylonians, the Egyptians, the Greeks, the Chinese, the Maya, the Aboriginal Australians, the peoples of the Pacific Islands, the indigenous cultures of North and South America. All of them developed their own star maps, their own constellation figures, their own mythologies of the sky. This universal human impulse to name and story the stars is remarkable. Whatever else divides human cultures, language, religion, geography, history, the habit of looking up at the same sky and finding meaning in the same points of light is something shared across all of them. The stars are, in this sense, the most universal of human reference points. Some of the star names we use today are the names given by ancient Arab astronomers, preserved in the Arabic translations of Greek star catalogues that were the primary astronomical texts of medieval Europe. When we say Betelgeuse, or Aldebaran, or Rigel, we are speaking Arabic, a reminder of the long cultural chain through which astronomical knowledge has been passed and preserved. The usefulness of Polaris as a navigational reference, its fixed position above the North Pole, its availability on any clear night, has been understood and exploited by Northern Hemisphere navigators for at least 2,000 years, and probably much longer. By measuring the angle of Polaris above the horizon, a navigator can determine their latitude with considerable accuracy. The angle equals the latitude directly. A navigator at the North Pole would see Polaris directly overhead. A navigator on the equator would see it on the horizon. A navigator at 45 degrees north latitude, approximately the latitude of Milan or Montreal, would see it 45 degrees above the horizon. This simple geometric relationship between Polaris's altitude and geographic latitude was understood and used by Greek, Arab, Viking, and Chinese navigators, among others. The stars made navigation possible across the open ocean. The stars connected the far parts of the world. In 1609, the Italian astronomer Galileo Galilei turned one of the first telescopes toward the night sky and recorded what he saw. Among his discoveries was that the faint, diffuse band of the Milky Way, when magnified, resolved into individual stars. Far more stars than could be seen with the naked eye, packed so closely together that their combined light created the appearance of a continuous glow. Galileo also observed that the stars, even through his telescope, remained point sources. They did not resolve into disks the way planets did. This observation correctly implied that the stars were vastly more distant than the planets, so far that even the enlarging power of a telescope could not resolve them into visible surfaces. His observations, published in 1610 in a small book called Sidereus Nuncius, the Starry Messenger, helped initiate the transformation of astronomy from a descriptive science of patterns in the sky to a physical science of bodies in space. The stars were not lights on a celestial sphere. They were distant suns scattered through an incomprehensibly vast space. For much of the early 20th century, the question of whether the faint spiral nebulae visible in large telescopes were objects within the Milky Way or distant island universes, comparable to our own galaxy, was one of the central debates in astronomy. In 1924, American astronomer Edwin Hubble resolved the debate definitively. Using the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble identified Cepheid variable stars in the Andromeda Nebula, and using Henrietta Leavitt's period luminosity relationship, calculated that Andromeda was approximately 900,000 light-years away. A modern estimate is 2.5 million light-years. The discrepancy reflects calibration improvements. This was far beyond the boundaries of the Milky Way. The Andromeda Nebula was not a nebula within our galaxy. It was a galaxy in its own right, a vast, independent system of billions of stars. The universe was not just the Milky Way. It was a universe of galaxies, of which the Milky Way was just one among billions. The scale of the cosmos, already almost incomprehensibly large, expanded overnight by a factor of millions. Launched in 1990, the Hubble Space Telescope, named after Edwin Hubble, has provided some of the most detailed and beautiful images of stars, stellar nurseries, and stellar remnants ever obtained. Freed from the blurring effect of Earth's atmosphere, Hubble can resolve details that ground-based telescopes cannot, and can observe ultraviolet and some infrared light that is blocked by the atmosphere. Among Hubble's most iconic contributions to stellar science are the deep field images, long exposures of tiny regions of apparently empty sky that revealed thousands of distant galaxies, each containing billions of stars, demonstrating the extraordinary depth and richness of the observable universe. The Hubble Space Telescope has given us images of the Eagle Nebula's pillars of creation, towering columns of gas and dust within which new stars are forming, that have become among the most widely reproduced astronomical images in history. They are images of stellar birth, captured with extraordinary clarity. Vast, quiet, beautiful places where the process that eventually led to everything we know is still ongoing. The rate at which new stars form across the observable universe has been declining for approximately 10 billion years. The peak of cosmic star formation occurred roughly 10 to 11 billion years ago, a time when the universe was younger, denser, and its galaxies were richer in the cold gas needed to form stars. Today, the star formation rate is roughly 10 times lower than it was at the peak. The universe is, in a very slow sense, winding down, gradually converting its reservoir of available cold gas into stars, gradually dimming as old stars die and are replaced by fewer new ones. Over the next several billion years, star formation will continue to decline. Eventually, on timescales of trillions of years, the last new stars will form. Then, only the very longest-lived red dwarfs will remain, burning for trillions more years in an increasingly dim universe, gradually cooling and fading until the last ember goes dark. The universe had its time of blazing star formation. We are living in the long, slow afternoon of that age. In the very deep future, tens or hundreds of trillions of years from now, long after the sun and every star in the current night sky has died, the only stars left in the universe will be red dwarf stars, burning slowly and dimly, but with extraordinary endurance. The least massive red dwarfs, those with about 8% of the Sun's mass, are calculated to have main sequence lifespans of approximately 10 trillion years, roughly 1,000 times the current age of the universe. They will continue to burn long after every other type of star has become a white dwarf, a neutron star, or a black hole. In the deepest future, the universe will be a place of scattered, widely separated red dwarfs, dim, red glowing embers in an increasingly dark cosmos, each one patiently burning on its last reserves of hydrogen, the final campfires of the stellar age. Following the death of the last red dwarfs, in the incomprehensibly remote future, perhaps 100 trillion years from now, the universe will enter what cosmologists call the degenerate era. The galaxy will be populated only by the cooling remnants of dead stars, white dwarfs slowly cooling toward black dwarfs, neutron stars, and black holes. Brown dwarfs, too small to have ignited fusion, will continue to drift through the dark galaxy, faintly warm but producing no significant light. Planetary systems, if any survive, will orbit in the dark around these cold, dark stellar remnants. This era will itself be followed by an even later phase, the black hole era, as protons eventually decay, if they do, and black holes slowly evaporate through Hawking radiation over unimaginably long timescales. But these events are so far in the future that they cannot be reached by any extension of human imagination. They exist only as the logical conclusions of the physics we currently understand. The stellar age, the brilliant, luminous era of nuclear burning stars, is a finite thing. It has a beginning, a middle, and an end. We are living near its middle. And the middle, as it turns out, is a very beautiful place to be. In September 2015, the LIGO Gravitational Wave Observatory detected the first direct evidence of gravitational waves. Ripples in the fabric of spacetime predicted by Einstein's general theory of relativity, produced by the collision and merger of two black holes, approximately 1.3 billion light-years away. In 2017, LIGO and its European partner, Virgo, detected gravitational waves from the merger of two neutron stars, the remnants of massive stars that had lived and died long ago. This event, designated GW170817, was also detected across the electromagnetic spectrum in gamma rays, X-rays, ultraviolet, optical, infrared, and radio waves. The first multi-messenger astronomical event ever observed. The neutron star merger was confirmed to produce heavy elements, including gold and platinum, through the violent R-process nucleosynthesis that occurs in such events. Gravitational wave astronomy has opened an entirely new window onto the universe, allowing us to detect events that produce no light at all, and to listen in a new way to the deep structural sounds of the cosmos. Before the first stars formed, in the cosmic dark ages that preceded the era of stellar light, the universe was filled with a hot, dense plasma that glowed uniformly in all directions. As the universe expanded and cooled, this plasma recombined into neutral atoms, and the radiation it emitted was released, free to travel unimpeded through the expanding universe. That ancient radiation is still traveling. It fills the universe today, diluted by 13.8 billion years of cosmic expansion to a temperature of just 2.7 degrees above absolute zero. It is detectable as the cosmic microwave background, a faint, almost perfectly uniform glow in the microwave portion of the radio spectrum, coming equally from every direction in the sky. The CMB is the oldest light in the universe, an echo of the universe as it was before the first star was born. It carries within it the seeds of all the structure that followed, the tiny density fluctuations that eventually collapsed into galaxies and stars. When we measure the CMB, we are looking at the universe before our own chapter began. While most binary star systems have orbital periods of days, months, or years, some close binary pairs orbit each other in extraordinarily short periods. The most extreme close binaries, pairs of white dwarfs or neutron stars, can complete full orbits in as little as minutes. H.M. Cancri, a binary system consisting of two white dwarfs, has an orbital period of approximately 5.4 minutes, the shortest of any known binary system. These two white dwarfs are separated by only about 8 Earth-Moon distances and are spiraling slowly toward each other, losing orbital energy through the emission of gravitational waves. Eventually, in millions of years, they will merge, potentially triggering a supernova or forming a single, more massive object. Until then, they continue their silent, rapid waltz, two small dead stars circling each other in the dark. Just as Earth has earthquakes, sudden releases of stress in the rocky crust, some neutron stars and white dwarfs experience analogous events called starquakes. In a neutron star, the incredibly dense and rigid crust can accumulate stress from changes in the star's rotation rate or magnetic field, and periodically release that stress in sudden fractures. When a magnetar undergoes a starquake, the rearrangement of the intense magnetic field releases enormous amounts of energy in a sudden burst of gamma rays and X-rays. These flares, called giant flares, can be detected across the galaxy and even, at their most extreme, from neighboring galaxies. The starquake that generated the 2004 giant flare from the magnetar SGR 1806-20 released, in about a tenth of a second, more energy than the Sun will emit over 150,000 years. That pulse of gamma radiation, arriving from 50,000 light-years away, was still intense enough to measurably affect Earth's upper atmosphere. The regions of space where new stars are born, stellar nurseries or HYY regions, are among the most spectacular objects in the universe. Clouds of gas and dust are ionized by ultraviolet radiation from young stars and emit light at specific wavelengths. The red of hydrogen, the blue-green of oxygen, and the deep red of sulfur create the colors seen in nebula images captured through specialized filters. Examples include the Orion Nebula, the Carina Nebula, the Lagoon Nebula, and the Eagle Nebula. In these regions, gas clouds collapse to form new stars, while young stars emit radiation and winds that gradually disperse the surrounding material. We noted earlier that a star's color reflects its surface temperature, and that temperature changes as the star ages. Over the main sequence lifetime of a star like the Sun, the gradual increase in luminosity also involves a slight increase in surface temperature and a subtle shift in color toward the blue end of the spectrum. In the red giant phase, the enormous expansion of the outer layers cools the surface dramatically, shifting the star's color through yellow and orange toward red. A star that was yellowish-white for 10 billion years becomes an orange-red giant, unrecognizable in its color compared to its main sequence appearance. The life of a star is a slow color story, a journey from the blue-white of a hot newborn through the stable yellow of a long main sequence life to the deepening red of old age. color as biography, light as autobiography. Stars are not passive. They continuously emit streams of charged particles, called stellar winds, which flow outward from the star's atmosphere at hundreds of kilometers per second. These winds carry material away from the star, gradually depleting its mass over its lifetime. The sun's solar wind continuously shapes the heliosphere, the bubble of solar influence that extends far beyond the orbit of Neptune and defines the boundary between our solar system and interstellar space. The interaction between the solar wind and Earth's magnetic field creates the auroras, the northern and southern lights, one of the most beautiful natural phenomena visible from Earth's surface. More massive stars have correspondingly more powerful stellar winds, capable of driving away significant fractions of their mass over their lifetimes. The most luminous stars lose mass so rapidly through their winds that they can shed many solar masses of material before they die, dramatically changing the properties of the stellar death that eventually follows. From a location with minimal light pollution on a clear night, the unaided human eye can see approximately 5,000 individual stars in the entire sky, though only about half of these are above the horizon at any given moment. In heavily light-polluted environments, this number can drop to only a few dozen. This 5,000 star view is the sky as essentially all human beings experienced it for virtually all of human history. No telescope, no photography, just the eye, the darkness, and the stars. The same stars that the people who built the pyramids looked up at. The same stars that guided the first people across the Bering Land Bridge. The same stars around which the world's mythologies were built. The loss of the dark sky to light pollution is one of the quieter cultural losses of the modern era. Not a tragedy of the same order as habitat destruction or species extinction, but still a diminishment. The stars have not gone anywhere. They are still there, exactly where they have always been. We have simply made it harder to see them. Stars appear to twinkle, to fluctuate rapidly in brightness and color, because their light passes through the turbulent layers of Earth's atmosphere on its way to our eyes. Different layers of air at different temperatures and densities bend and refract the light slightly differently as they move and mix, causing the apparent position and brightness of the star to fluctuate rapidly. This twinkling, technically called scintillation, is most pronounced for stars near the horizon, whose light must travel through more atmosphere to reach us, and least pronounced for stars directly overhead. Planets twinkle much less than stars, because they appear as small disks rather than points. The random fluctuations average out across the disk and become less visible. Astronomers who observe from space, or who use adaptive optic systems that correct for atmospheric turbulence in real time, see the stars as steady, unwavering points of light, exactly as they actually are. The twinkling is entirely a property of our atmosphere, not of the stars themselves. But it is beautiful, and it has been watching people fall asleep for as long as people have been falling asleep under open sky. While pulsating stars change brightness due to internal processes, other variable stars vary because of interactions with a binary companion. Eclipsing binaries, pairs of stars aligned with our line of sight, cause regular dips in brightness as one passes in front of the other. Algol is an example, with brightness dips every 2.87 days when the fainter star passes in front of the brighter one. This variability was noted by Arab astronomers, and its name means the ghoul, or the demon. The regular light variations of eclipsing binaries reflect their orbital motion, with each dip corresponding to one star passing in front of the other. The warm red and orange colours of the sun near the horizon at sunset, the colours that make sunsets among the most universally appreciated natural phenomena, are caused by the same physics that gives stars their colours. Light at the red end of the spectrum has a longer wavelength and is less scattered by the atmosphere than blue light. As the sun approaches the horizon, its light must travel through more atmosphere, and more of the blue light is scattered away, leaving the red and orange wavelengths dominant. The blue sky of the day is the blue light that was scattered. The red sky of sunset is the red light that wasn't. Both are the same sunlight, separated by the selective filtering of the atmosphere. This same principle, that different wavelengths of light behave differently in different media, underlies all of stellar spectroscopy, all of our ability to determine stellar temperatures and compositions from their light. The physics of a sunset is the physics of the universe's most powerful diagnostic tool. The photons created by nuclear fusion in the sun's core do not travel directly outward. They undergo repeated absorption and re-emission in the dense solar plasma, following a random walk through the interior. This journey through about 700,000 kilometers of plasma takes on average around 100,000 years, though estimates vary. The light reaching Earth today was produced in the sun's core roughly 100,000 years ago, traveled slowly through the sun, and then crossed about 150 million kilometers of space in about 8 minutes before reaching Earth. It is an extraordinary thought. Sunlight is not instant. It is history. The death of a star is also a beginning. The elements formed in a star's life and in its death are scattered into the interstellar medium, becoming material for new stars. Each generation of stars enriches this material with heavier elements. The first stars formed from hydrogen and helium, while later stars, including the Sun, formed from gas enriched by previous generations. Future stars will be even more enriched, supporting complex chemistry and life. This ongoing cycle of formation, death, and rebirth has continued for about 13 billion years, gradually increasing the universe's chemical complexity. Among all environments in the universe, stars are the primary sites where elements heavier than helium are created through nuclear reactions. Without stars, the universe would consist mostly of hydrogen and helium, with no rocky planets, no liquid water, no organic molecules, and no known basis for life. Everything we observe, from rocks to living organisms, depends on the existence and life cycles of stars, which produce and distribute the elements that make up all matter. Stars are therefore essential to the existence of complex structures in the universe, producing elements over billions of years through their formation, evolution, and death. Since the discovery in 1998 that the universe's expansion is accelerating, driven by dark energy, which makes up about 68% of the universe, astronomers understand that the future universe will become increasingly isolated. As expansion continues, galaxies beyond the local group, including the Milky Way and Andromeda, will recede faster and eventually move beyond our cosmic horizon, becoming invisible and inaccessible. Stars in distant galaxies will effectively disappear from our observable universe, while only stars within our own gravitationally bound galaxy will remain visible. We live in a time when many galaxies are still observable. Future observers will see a much darker and more isolated universe. In approximately 5 billion years, when the Sun finally sheds its outer layers in the planetary nebula phase, the resulting expanding shell of gas will be visible, briefly on astronomical timescales, from considerable distances across the galaxy. For perhaps 10,000 years, any sufficiently sensitive telescope on a planet in a star system within a few thousand light-years would be able to detect the Sun's nebula, a small, faint, expanding ring of glowing gas, the final exhalation of a middle-aged star. Then, the nebula will disperse, and the Sun's remnant, a slowly cooling white dwarf, will be detectable only at very close range. The Sun will leave a mark on the galaxy, not a large mark, not a lasting one by cosmic standards, but real and detectable. A small monument of light, briefly visible to anyone who might be watching, before fading into the general enrichment of the interstellar medium. We have circled around this idea several times tonight, but it deserves a direct and complete statement. Human beings, all life on Earth, in fact, are made possible by the deaths of ancient stars. The carbon in your DNA, the oxygen in your lungs, the iron in your blood, the calcium in your bones. All of these elements were created inside stars that lived and died billions of years before the Earth existed. They were scattered into space by supernova explosions. They drifted as interstellar gas and dust for millions of years. They were gathered by gravity into the cloud that became the solar nebula. They condensed into planets. Over billions of years of geological and biological evolution, they became, among many other things, you. You are not separate from the stars. You are made of them. Your body is the current address of atoms that have been in nebulae and stellar cores and supernova and interstellar clouds and oceans and organisms and rivers and rock. You are the universe's current form for those atoms, temporary, local, improbable, and extraordinarily precious. For virtually all of human history, no one knew what the stars actually were. They were lights, they were signs, they were gods, or the abodes of gods, or the souls of the dead, or points on a celestial sphere. But no one knew they were distant suns, massive, luminous spheres of plasma engaged in nuclear fusion, scattered across a vast galaxy. The understanding of stars as distant suns, and the understanding that the sun itself was a star, developed gradually through the work of astronomers from Copernicus and Galileo, through Newton and Herschel, and into the 20th century. The full picture of stellar physics, the understanding of nuclear fusion as the source of stellar energy, the stellar life cycle, the role of supernovae in creating heavy elements, was not complete until the mid-20th century. We are, in this sense, among the first generations of humans to actually know what the stars are, to look up at the night sky and understand, in some meaningful physical sense, what we are looking at. This knowledge is very recent and very hard-won and very beautiful. It changes what the stars mean, to us and through us. The overview effect is a shift in perspective reported by astronauts who view Earth from space, seeing it as small and fragile against the cosmos. A similar perspective can be gained by observing a dark night sky. Under the stars, daily concerns can feel smaller, not because they are unimportant, but because they are seen within a much larger context. The stars have existed for billions of years and will remain long after present concerns are resolved. Observing them can provide a sense of proportion rather than escape. The astronomer and science communicator Carl Sagan popularized the phrase, "We are made of star stuff," in his 1980 book, Cosmos, expressing the scientific fact of stellar nucleosynthesis in a clear and accessible way. He interpreted this as a way of understanding humanity as part of the universe, suggesting that the cosmos has become aware of itself through human beings. The elements in the human body were formed in stars. This is a scientific fact based on stellar nucleosynthesis, not a metaphor. Launched in December 2021 and fully operational by mid-2022, the James Webb Space Telescope, the most powerful space telescope ever built, has provided unprecedented views of stars, stellar nurseries, and the earliest galaxies in the universe. Its infrared sensitivity allows it to peer through the dust clouds that obscure star-forming regions, revealing the young stars forming within them in extraordinary detail. Webb's first images included a stunning view of the Carina Nebula, a stellar nursery about 7,600 light-years away, that showed hundreds of previously unseen young stars emerging from the gas and dust of the cloud that birthed them, their radiation beginning to sculpt the nebula's edges. It also revealed details of stellar death in the Southern Ring Nebula with previously impossible clarity. Webb is designed to detect light from the very first galaxies, the earliest stellar populations to form after the Big Bang, providing a window into the universe's first few 100 million years. It represents our most powerful current tool for understanding stars at every stage of their lives and across the full span of cosmic history. The universe emits radio waves from stars, stellar remnants, gas clouds, and galaxies. And radio astronomy reveals phenomena not visible in optical light. Pulsars were discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish as highly regular radio pulses, initially labelled LGM1 before their natural origin was understood. Interstellar molecules, including complex organic ones, have also been detected through their radio emissions in star-forming clouds. The hydrogen spin-flip transition allows mapping of neutral hydrogen across the Milky Way, revealing its structure and the material for future star formation. Radio waves can pass through dust that blocks visible light, exposing regions of space otherwise hidden to optical observation. The nuclear fusion reactions in stars produce enormous quantities of neutrinos, nearly massless, electrically neutral particles that interact very weakly with matter and pass through most materials almost unaffected. Approximately 65 billion solar neutrinos pass through every square centimetre of your body each second, passing through the Earth with almost no interaction. In a supernova, about 10 to the power of 58 neutrinos are released, carrying more energy than the combined light output of all stars in the observable universe for a short time. In 1987, a supernova in the Large Magellanic Cloud was detected by a burst of neutrinos, observed before the visible light because neutrinos escape directly from the collapsing core. The universe continuously passes through you in the form of neutrinos emitted by stars. The surface of the Sun, when observed through a solar telescope, is not a smooth, featureless disk. It is covered in a constantly churning pattern of cells, convection cells called granules, each one roughly the size of Texas, lasting for about 10 minutes before dissolving and being replaced by new cells. These granules are the tops of convection currents in the outer layer of the Sun. Columns of hot gas rising from deeper layers, spreading laterally at the surface, cooling and sinking back down at the boundaries between cells. The overall effect is like a vast, slow-moving, planet-scale pot of boiling water. Endlessly churning, endlessly renewing, restlessly carrying heat from the solar interior to the surface. Larger-scale convection patterns, supergranules spanning thousands of kilometers, create currents that transport magnetic field to the solar surface, concentrating it into sunspots and active regions. The sun's surface is alive with motion, even though from Earth it appears simply as a smooth, featureless disk of light. Scattered around the Milky Way in a roughly spherical halo are about 150 to 160 globular clusters, dense spherical collections of hundreds of thousands to millions of stars orbiting the galactic center. The stars in globular clusters are among the oldest in the galaxy. Many formed more than 12 billion years ago and are metal poor, reflecting early conditions in the universe. Globular clusters are ancient groups of stars, tightly bound and long-lived, containing some of the oldest stars still burning in the Milky Way. The night sky visible from Earth today, with its specific stars, constellations, and planetary positions, is unique to this moment in cosmic history and has never been exactly the same before. Over thousands of years, stellar motions will change constellations. Over hundreds of thousands of years, stars like Betelgeuse may explode as supernova, and over billions of years, the galaxy's star arrangement will be completely different. The sky above you tonight is a singular snapshot of this time, place, and history, and it will not exist in exactly this form again. We have followed the life cycle of stars, from their birth in nebulae to their deaths as planetary nebulae and supernovae, and learned about giants, dwarfs, pulsars, black holes, globular clusters, and stellar nurseries. The elements in our bodies were formed in stars, and some of the light we see left its source before humans existed. The universe is still forming stars, and it will continue for trillions of years. You are part of this process. The atoms in your body originated in stars and will return to space and eventually form new stars. You are a temporary arrangement of these atoms, a brief moment in the universe's ongoing cycle, aware of itself. This is the story of the stars, and it is also your story. We have traveled through a vast and ancient universe tonight, from the cosmic dark ages before the first star ignited, to the last dim red dwarfs burning in the far future, trillions of years from now. We have passed through nebulae and supernova remnants, through binary stars and planetary systems, through the cold dark between galaxies and the warm, active surfaces of stellar nurseries. Along the way, we have learned something that may, with the passage of the night and the settling of these facts into something quieter and more felt, be one of the most remarkable things human science has ever discovered. That we are not watching the stars from outside as observers of something separate from ourselves. We are, in the deepest chemical sense, part of the stellar story. We are the cosmos, having become briefly, improbably, beautifully aware of what it is. The stars have been burning for 13 billion years without any witness. Then, relatively recently, on one small planet orbiting one ordinary star, something happened. The universe developed the capacity to observe itself, to wonder, to measure, to feel something. Something like awe, something like peace, something like the quiet satisfaction of understanding. When it looks up at its own night sky, we are that capacity. We are temporary, brief, and fragile by cosmic standards. but we are real, and we are here. And on this particular night, we have spent a few hours in the company of the stars. That is not nothing. That is, in fact, extraordinary. Let the facts settle now into something softer and less structured. Let them dissolve from information into impression. The first stars, enormous and brief, lighting the darkness of an empty universe. The patient red dwarfs, burning for trillions of years, outlasting everything. The red giant swallowing its inner planets. The planetary nebula expanding into the dark. The supernova, bright as a galaxy, scattering the seeds of new worlds. The neutron star, spinning hundreds of times per second in the silence between stars. The ancient globular cluster, hundreds of thousands of old suns orbiting together through the halo of the Milky Way. The light of Andromeda, 2.5 million years old, arriving at your eye. The granules churning on the sun's surface, each one the size of Texas, each one lasting 10 minutes. The solar neutrinos passing through you, tens of billions per second, continuous and indifferent, and carrying the news of the sun's ongoing fusion. The carbon in your cells, made in a red giant. The iron in your blood, forged in the death of a massive star. The oxygen in your lungs, scattered by a supernova. All of it drifting through the interstellar medium for hundreds of millions of years before the solar nebula gathered it, and time and chemistry made it you. The night sky unique to this moment. The particular arrangement of stars that no one before you has seen quite this way, and no one after you will see again. Yours for tonight. Now let all of that go. Let the images soften. Let the numbers dissolve. Let what remains be simply this, a quiet sense of the sky above you, vast and ancient and full of patient burning light. Feel the weight of your body where you lie, the small warmth of your own breathing, the stillness of the room around you. Somewhere above the ceiling, above the roof, above the clouds and the atmosphere and the thin skin of air that separates us from the cosmos. The stars are out, the same stars that have been there every night of your life, the same stars that were there before you were born and will be there long after you are gone. Patient, brilliant, burning. They do not need anything from you tonight. They simply burn as they have always burned, steady and quiet and indifferent in the best sense, in the sense of being simply, completely what they are. And you are warm and horizontal and no longer required to understand anything or do anything or be anything in particular. You are just here, in this moment, in this body, in this small, warm place, while the enormous universe goes quietly about its business above you. Let your breathing become a little slower. Let the exhale be a little longer, a little more complete, a little more like letting go. You are made of stardust. This is true. And right now, this particular arrangement of stardust is tired and warm and ready to rest. Let the stars burn in their silence. Let the universe expand in its long, slow, patient way. Let all the neutron stars spin, and all the nebulae drift, and all the red dwarfs glow their dim, eternal red. None of it requires your attention tonight. You can simply rest. Let your thoughts become slower. Let them become less distinct. Let the ceiling become the sky, and the sky become stars, and the stars become just light. Quiet, distant, ancient light. And let even that dissolve into the warm, dark, restful nothing of sleep. If tonight's journey through the stellar universe brought you some peace or some wonder, we would be quietly grateful for a gentle like or a subscription before you drift away. so that future nights can bring you more long, slow, beautiful journeys through the most remarkable things science has yet discovered. There are many more evenings waiting, through oceans and forests, through the microscopic and the cosmic, through the lives of creatures and the histories of worlds. But for now, there is only this: the quiet dark, the slow breath, the stars, doing what they have always done. Sleep well. Good night.